Okay, so no school tomorrow. I think that's just a Normandale thing. So if you have any classes anywhere else, you better check on that. Don't just assume that it's not going on at MCTC or whatever. But then Wednesday is exam 3. And the topics are everything up through particle kinetics, number 9. What that means is basically there will be pulling with cables. So there'll be, weight force, pushing forces, and then pulling with cables, but not including any pulleys. It, it could have that. Um, oh, it was? That first one was, okay, well, then yes, you're right. There will be no slants, uh, but no pulleys. Yes, that's right. All of these are cumulative. So you want to, glance back at the old stuff and make sure you remember that somewhat.
Are there going to be like, for example, sometimes where we have 30-degree?
I just found out that there will not be anything like that. I thought maybe there would, but there's not. Okay. Okay. Well, that's good. No, no inclines. Yeah. I haven't written a test yet. It's like, I haven't never written a test a day ahead of time. What if physics changes? um, any other questions about the test?
It'll be circular motion, like in the circular motion
Yeah.
for like the if the center is fixed, you give us saying like what is the for the vector on top and then a vector for the bottom? Like,
Yeah, that stuff is reasonable to ask questions about. So the next topic that I want to discuss, uh, it just goes a little farther with pulling with cables, and it starts dealing with pulleys also. That is not on the test, like I said. So if anybody has any homework questions or anything related to the test, I'd be happy to go through that as long as you want. Kevin and Knight, sure. Okay, so this is a cool one. Number 7 is a motorcycle does a loop-de-loop on a circular path. The radius is 2 meters. And at the top of the circle, the motorcycle speed is not changing. That's what would happen if there was no friction or anything and it was just coasting because the height isn't changing. So staying at a constant speed for that instant at the top is a pretty reasonable assumption. And the speed has a value of 15 meters per second. That's probably pretty fast. Okay, so there's the motorcycle. And at this instant, speed is 15 meters per second, and it's constant. That doesn't mean that it's constant going from this point to this point. It just means right at that instant the speed isn't changing. And the motorcycle and rider together is 350 kilograms. That's probably a little high, I suppose, but that's what we're using. Sketch the system. So I already did that. What's the total acceleration vector of the motorcycle at this instant? What's the net force at this instant? And what's the force applied to the motorcycle by the path, by the loop at that instant? Okay, so if we're treating, so let's say the path is of the center of mass is this. At this instant, the velocity vector is this. Speed isn't changing, so there's no tangential acceleration. The centripetal acceleration is this, and that's also equal to the total acceleration. Magnitude of the centripetal acceleration is omega squared r. But remember, that's usually what we use, and we could figure out what omega was. Remember that we also know that the speed is equal to omega r. And so we can combine these two. And the centripetal acceleration then can be calculated as the speed squared divided by r. So you can think of the magnitude of omega as speed over r, and then plug that in here, and that's what you get when the stuff cancels. And so you get 15 squared over 2. So that's, what's that, 112.5? Oh man, that's a big acceleration. Okay, well, the total acceleration in this case is just the centripetal acceleration. It's in the negative y direction. So 0, negative 112.5. That's meters per second squared. And as someone pointed out before, over 100 meters per second squared is blackout territory. I think when you watch those, I was just coming up with those numbers by imagining what I've seen at like the Barnum and Bailey circus. I think my radius is too small and my speed is too big, and those both increase the acceleration. But anyways, so we have this. And now the net force is just equal to the mass times the acceleration. And so what do you get? 375? Wow, that's a lot. And this is a vector, so that's 0 for x, and then that's the net force for y. then we want to calculate the force vector applied by the contact at this instant. So for that, we would draw a free body diagram. So here's the motorcycle and the rider. So there are two forces acting. There's a weight force. So that's 350 times 9.81. What do you get for that? $34, 33.5. And then there's a contact force on the wheels. If we just think of that as a pushing contact, I'll write that as a normal force. Then Newton's second law, we have 0, negative n, plus 0, negative 3433.5 is equal to the net force that we just calculated, but I'm going to do it again as the mass times the acceleration. The x equation doesn't give us anything. The y equation says negative n minus 3433.5 is equal to negative 39,375. And so n is equal to 5 4 1.5, something like that. And then if you want to calculate the force vector that's applied to the motorcycle by the path, this is it. And so the force vector on the wheels by the path, plug this number back into that vector and you get 0, negative 35,041.5 newtons. Divide that by 4 and you get the force in pounds, so that's a little under 10,000 pounds or something. Okay, question?
For the normal force, that's like the bike is like the loop, that means the normal force is going to go negative.
Yeah. Yeah, because that's a pushing force, and pushing forces always are perpendicular to the surface of contact toward the chosen body. And so that's how we knew the direction. Well, it happens to be in the same direction as a centripetal. That would not be the case if we were looking at the bottom, you know. Let's do another question about this, because these kind of problems come up pretty often. What's the slowest the motorcycle could go and not fall off of the path at the top? Okay, so if something doesn't make it around the loop, you know, place where it's most likely to happen is right at the top, because that's where you've slowed down the most, and that speed is what holds you to the side. So let's say, what's the minimum speed at the top so the wheels stay in contact with the path? Okay, so let's think about this idea again. but this time we don't know the speed. We're trying to find it. Okay, so the centripetal acceleration magnitude is v squared over r, and that's just 1/2 v squared. So what we're going to calculate is that speed. Okay, and we still, all the directions are the same. We're still looking at the same instant. So the centripetal acceleration as a vector is it's in the negative y direction. So that's 0 for x, negative 1/2 v squared for y, and that's the total acceleration. Anybody have any questions? I skipped redrawing all this stuff, but the idea is it's just like this, except now we don't know what this 15 meters per second is. We're going to calculate that speed, and so we're just leaving it in here as v squared over r, and the r is 2, so but all the directions are the same. So now we have an acceleration that depends on the speed. That's the expression. And then we'll draw the free body diagram. It looks just like it did before. You can never have too many free body diagrams. And the forces are the same. You still have a weight force that's 350 times 9.81. So that's a downward force of 3433.5. And you still have a pushing contact, N. And we can write this in Newton's second law. We get 0, negative N, plus 0, negative 3433.5 is equal to the mass times the acceleration. So that's 0 for x, negative 1/2 v squared for y. The x equation doesn't give us anything. The y equation says negative n minus 3433.5 is equal to negative 175 v squared. All right, well, that's one equation with two variables. So we can't solve it without thinking a little more about it. So now we have to think, what does it mean for this thing to maintain contact with the top? Yes, so if for it to maintain contact with the top, there has to be a positive value of this n. Okay, so like the limit of, so the absolute smallest value for n that you could have and have this maintain contact with the top is 0. Okay, so if we're trying to find the smallest speed that will allow this to stay in contact, we're going to set this equal to 0 and calculate that v. Think about it this way: if that n went from 0 to like negative 0.1 or whatever newtons, that's saying that when this gets to the top, in order to maintain that circular motion, the top has to be pulling up on the wheels. Okay, it has to switch from pushing to pulling, and that the top can't do that, and so that's the instant where it would fall off of the path. And so now we have 3433.5 is equal to 175 v squared. Can someone calculate that v?
.43.
4.43 meters per second, plus or minus. It's a speed, so we want the plus. So yeah, about a little over 10 miles an hour. If it's not going at least 10 miles an hour at the top, it's going to lose contact at the top. Any questions about that one? Okay. And then number 9. At time equals 0, the position is a 0 vector, and the velocity is a 0 vector. So the thing starts at rest and it starts at the origin. And the net force on the object can be written as a function of time. And that's equal to t negative 3t. And we want to know what's the position vector as a function of time. Well, Newton's second law says there's a relationship between the net force and the acceleration. So Newton's second law says t minus 3t is equal to, we're not given a mass, so we're just going to have to include the mass as a constant. This is equal to the object's mass times its acceleration function. I'll write that as ax, ay. And then we're going to solve for those two accelerations. So the x equation says ax as a function of time is equal to t over m. And the y equation says ay as a function of time is equal to negative 3t over m. T is a variable. And m is a constant. But now we have a kind of problem that we've done before. We have functions representing the acceleration, and we need to come up with a position function. Any questions about using Newton's second law to go from net force to acceleration? Yeah. We have two equations here. One says t is equal to m ax, and one says negative 3t is equal to m ay, and then we just solve it. Okay, so I'm going to start with, so now we're just going to, integrate the acceleration as a function of time. The acceleration is the time derivative of velocity, so we know that dvx dt is equal to T over M. And so dVx is equal to T dt over M. And now you can just integrate both sides. And you get V as a function of time is equal to T squared over 2M plus C1. And now we use a boundary condition to find C1. The boundary condition says at time equals 0, Vx is equal to 0. And so this equation gives us 0 is equal to 0 squared over 2m plus C1. So C1 is equal to 0. So now we have the function, the velocity function for the x component. V of x is a function of time is equal to t squared over 2m plus 0. And now the x component of the velocity is the time derivative of the x component of the position. So dp dt is equal to t squared over 2m. So dp is equal to t squared over 2m dt. Integrate both sides. And you get that p of x as a function of time is equal to t cubed over 6m plus a constant. And we have another boundary condition that says when time is equal to 0, px is equal to 0. So this equation, if you plug those both in, says 0 is equal to 0 cubed over 6m plus c2. So c2 is equal to 0. So the x component of position is equal to t cubed over 6m. And then you do the same thing with the y component. Anybody want to see me do it with the y component? It's the same steps. But then at the end, once you have px as a function of time and py as a function of time, then those are just the two components of your position function. Any questions about that one? Any other homework questions anybody wants to see? Okay. Yeah.
I know I understand the problem, but just want to like.
Yeah, sure. I'd be happy to go through as many of these as you want. A car accelerates backwards. As a coffee cup inside falls. And so first, the acceleration of the cup according to an observer, like on the street. Second, what's the acceleration of the cup to an observer inside the car? Three, which of these coordinate systems is suitable for using Newton's second law? And last, use Newton's second law to find the net force on the coffee cup. The idea of this problem is a couple of these questions are ones where you sort of know the answer ahead of time. So it's sort of a way to make sure that your mathematical steps are working with reality. Okay, so this coffee cup is in free fall. So compared to the ground, to the observer on the street, it's just accelerating downwards at negative 9.81. That's not going to be what the observer inside the car sees. We'll calculate that. And so if you think of a coordinate system as being video camera, okay, that's measuring the motion of things. The observer inside the car and the observer on the street, you can think of both of those as coordinate systems. They're both observing what's happening. The coordinate system on the street is suitable for using Newton's second law because it's an inertial reference frame. It's not accelerating. Well, like we talked about last time, it's accelerating a little because the Earth's rotating, but very, very little. The car is accelerating a lot. And so you can't use a coordinate system whose origin is accelerating. So the cars as a reference frame is not an inertial reference system, a coordinate system. And so the acceleration you measure in the car, that won't work with Newton's second law. Okay. Well, what we should get if we choose the right one of those coordinate systems is if something's in free fall, the net force acting on it is just mg down, right? We know that. That's what free fall is. So once we make our choices and do the calculations and whatever, even without a solution, we should know whether our answer is right or wrong. Doesn't give a mass, so we'll just leave the free fall acceleration is, we'll call it G, pointing down, and the mass of the cup is M. All right, so the acceleration of the cup relative to the ground is equal to the acceleration of the cup relative to the car plus the acceleration of the car relative to the ground. One of these three is going to have component 0, negative 9.81, or 0, negative g. Which one of these? Cup relative to ground. Yep, so this is 0, negative g. If you did that as 0, negative 9.81, that's true. That's right too. I'm just leaving it as a constant g. And now one of these is, if backwards is in the negative x direction, one of these is negative 4, 0. uh, in the negative x direction. Which one is that? Car relative to the ground. So this is equal to the acceleration of the cup relative to the car plus negative 4, 0. And do the algebra, and you get that the acceleration of the cup relative to the car is 4 negative g. So what we're talking about is there's a couple of ways, like physically, there's a couple of ways that a car could accelerate backwards. One is it could be at rest and you could slam in reverse and accelerate backwards. And the other way is you could be driving forward and slam on the brakes. Either one of those has a backward acceleration. So let's imagine you're driving down the street and you slam on the brakes. Yep. Yes.
So the car, like it's slowing down, it's not going backwards, but the stuff it's going to always fly.
Yes. So what's going on there is your velocity is in the positive x direction. And so to slow down, your acceleration has to be in the negative x direction. Okay. And what you see when you do that is everything that was on your dashboard and on the console appears to accelerate forward. That's what we calculated there. The coffee cup looks like, if you don't know anything about what else is happening, you're just watching a video looking at your console. You just out of the blue see a coffee cup accelerate forward and smash into the dashboard, you know. And that's what we calculated. The acceleration to somebody, so that's what it looks like to a video camera inside the car. To a video camera that's on the street watching it go by, you just see this coffee cup that had an initial velocity equal to the car's starting velocity go into a parabolic motion, a free fall motion. Yeah, right. That's right. It'll look like a projectile motion, because if the car is starting at 20 miles an hour and it hits the brakes, the coffee cup is just a projectile that started at 20 miles per hour and now is in free fall. Okay, which of these is suitable for using Newton's laws? You can't use Newton's laws. So you can only use Newton's second law for non-accelerating coordinate systems. So only the acceleration of the cup relative to the ground works for Newton's second law. And so if you do that, then Newton's second law says 0 negative g is equal to the mass of the cup. Sorry. This left side is the forces. So this should be F net is equal to the mass times the acceleration relative to the ground. So 0 negative g. And so the net force is 0 negative mg. And that makes sense. Something in free fall, the only force on it is the weight. If you use the other force, you'd think that there was this additional horizontal force of positive 4m that doesn't make any sense with free fall. And so you see that Newton's second law fails if you use this non-inertial coordinate system. Any questions about that? Any other homework questions? It's probably too late to start any new stuff. So, are there any others anybody was hazy on? Yeah.
When I started doing number 7, I didn't know what loop to loop.
Oh, okay, yeah.
So I did it on the
Oh, horizontal, yeah.
Yeah, and I have like
Yes.
so I didn't like
Right.
I was confused between the end and the way
Yeah.
going it on. I ended up with different results.
Okay. Let's
You know,
yes. Let's calculate that. So the net force is going to be exactly the same. So number 7 reprise. What if the loop was parallel to the ground? Well, you still get that the acceleration vector is whatever we got before, that really big acceleration. Negative 112.5. And the net force then is just equal to 350 times that acceleration. So nothing's changed yet. The net force is still just 0, negative 39,375. Then when you do your free body diagram, now the weight force is into the page, 3433.5. And you'd have a normal force like this. And if we're just doing this in 2 dimensions, which is, you don't have to do any thinking in 3 dimensions in this, you would just see that now Newton's second law says 0, negative n is equal to 0, negative n is equal to 350 times 0, negative 112.5. And the weight now doesn't interact with that normal force. So the normal force is just equal to 39,375. There is something sort of interesting going on out of the plane. You don't really have to worry about that, but if you're curious about it, the only way that this could keep going horizontally like that is if there are 2 possibilities. One is that it's going fast enough that normal force generates friction that keeps it from sliding down. You know, there's nothing about, no matter how fast you go this way, there's no centripetal acceleration that's keeping you up, you know? So there are two possibilities for what keeps you up. One is that you go fast enough that that normal force gets big, and then that produces, we'll talk about mathematically how this works, but that produces enough friction that you don't slide down. And then the other one is just that that ramp is a little bit banked. And so there's a little bit of a component of normal force up, and that's enough to keep it from sliding down. Any other questions about that one? Okay, well, have a good day off tomorrow. If you have any questions, email me and I'll try to answer. It's kind of hard to ask email questions related to math stuff, so I would recommend if you do have a question, just take a cell phone picture of whatever you're working on, the solution or whatever. It'll make it easier for us to communicate back and forth. And then test on Wednesday. Thank you. Thanks.